Well, I'll get started. Begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for this class. And just we ask you to guide our steps today. Help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So today we are talking about the RC circuit, or RC circuits, and so we'll look at a few different ones of these, and we'll figure out how to solve these. Your brief vacation from calculus has come to an end, because we will need calculus for this. So I'll start out with the most basic of all such problems, which is the discharging capacitor. So we suppose we've got a capacitor and got some switch, basically, and you've got a resistor like so. All right, resistor R, capacitor C. And what we want to do is we want to imagine that we've charged the capacitor, all right, with a charge of Q on it. And so like we've prepared, so the starting point, initial condition. The initial condition for us is that the charge at time 0 is, let's say, Q naught. So you've got charge Q naught on the capacitor, all right? So I'll just say Q here for capacitor. Charge on the capacitor. Of course, if we got Q there, we got minus Q here. You know the deal. Then we're going to, close the switch at t equals to 0. All right, so like that. So this is closed for t equals 0 plus. It's closed. All right. And once we do that, then what happens? Then the charge which was on the capacitor, right, it can flow off the capacitor plate like that with a current, let's say I, right? And so what can you tell me? If the current is flowing that way, like that, right? You go plus, minus. Of course, over here you got minus, plus. The point is that what was the relation between voltage and charge on the capacitor? How's it go? Capacitance is what? Yeah, Q over V, right? So the voltage on the capacitor should be equal to the voltage on the resistor, right? So we have Q over C is equal to IR, all right? And then, like, well, how do we solve this? Well, what's the relation between the current and the charge on the capacitor? Can you guys tell me? R times what? I equals what? So what's happening as the current flows, the charge is changing, right? Is it increasing or is it decreasing here? Yeah.
I staying constant, isn't it?
No. No. I is varying here. It's decreasing, right? So for that reason, we say I is minus dq dt. Which, if I forget about that sign, I get like super confused in the calculus that follows, because I'll work it out and I'll be like, whoa, after the discharging capacitor has like a charge which just keeps building up as time goes to infinity. That's weird. Yeah, so that minus is important. It's quite important, as we'll see here. So what we're up against, right, guys, is Let me rewrite this. We've got, I'll just write it again. Q over C is equal to minus R dq dt. How do we solve this? You guys have had calculus too. You should know how. What I'm going to do is I'm going to divide the R to the other side. I got myself a dt over RC with a minus equals dq over q, right? Separate, integrate, right? And since I know about time 0, I'm going to integrate from time 0 to, let's say, the final time. And I'm going to integrate from the initial charge q naught to the final charge qf, right? Matching bounds. And so that gives me minus the final time divided by RC is equal to the natural log of the absolute value of qf minus the natural log of the absolute value of q naught. But I can solve this. This gives me, of course, minus t over RC is the natural log of the absolute value of the quotient of the final charge to the initial charge, which if I exponentiate both sides, what do I get? I get the absolute value of qf over q naught equals to e to the minus t over RC, which, if we think about it for a second, is going to give us q at time t is equal to q naught e to the minus t divided by RC, where I've taken the liberty of saying q of t is the final charge. Right. Now you can check my formula. Does it make sense? If we plug in t equal to 0, what do we get? Q sub naught, right? Which is what we're supposed to get. The charge at time 0 is supposed to be q sub naught. And then we've got this exponential, right? So definition, tau equals to RC is the so-called time constant. For the RC circuit. And so if I graph what's going on here, here's time, here's charge, here's the initial charge q naught, here's 1 time constant, 2 time constants, 3 time constants, 4 time constants, 5 time constants. What's the graph look like for charge as a function of time here? Get my calculator out here so I can give you some digits. So we can take our handy dandy exponential and feed it -1, and that gives me 0.36. So after 1 time constant, I'm bound to about here-ish. That's about 0.37 q naught. All right. If I square that, that takes me down here to about 0.14 q naught, about 14% of the initial charge at 2 time constants. All right. What do we got at 3 time constants? How much of the initial charge remains at 3 time constants? We got about 5%. Only about 4.9% of the charge remains after 3 time constants. How much charge remains on the charged capacitor after 4 time constants? 1.8%, 0.018. It's going to get really hard to see these difference between these and the axis at the limit of my artistry. By the time you're to 5 time constants, Where are we at? That's e to the minus 5. Oops. E to the minus 5 is equal to, whoa, I'll just write it down here. E to the minus 5 is equal to 0.000674. Right? So by the time you get to 5 time constants, you're like less than 1% of the charge. No, less than 0.1% of the charge is still left on the capacitor. Right? So for that reason, essentially, for an RC circuit, the time at which the circuit is dynamical, in other words, the time at which the circuit is time varying, where it's changing, is 5 time constants is essentially a lifetime. Everything interesting with the circuit in terms of the dynamics of it, it's happening in the first 5 time constants. Honestly, really just the first 2 time constants, right? This is already at like 10%. 3 time constants, by 4 time constant, you're very close. 5 time constants, you're less than 1% of the charge is left. And of course, do you ever get to 0 charge? No, right? So there it is. That's the formula for the charge on a discharging capacitor. Question. So the current was constant, right? Is the current constant? What's the current? Let's work it out. What's the current then in this situation? Minus dq dt, right? Which is what? Minus ddt. Uh-oh. 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 Q naught e to the minus t over rc, which when we differentiate, what do we get?
Q over C exponential negative T over RC.
Very good.
I read your notes.
Oh, you read my notes? That seems like cheating. Maybe I should read my notes. Let's see here. Some days it would be an improvement for sure. But look, so is that different than the graph which is given? I mean, in terms of shape, not really, right? So if I was to graph, I could make a comment. No, this kind of graph is dangerous because, it's got different things on it. But this is the graph of current Q naught over RC, right? If I was to try to graph on the same plot, like, and this is kind of a crazy thing to do, to graph things with different units on the same graph, but sometimes we do this, right? If you think back in calculus, we do show you like graphs of velocity and position and acceleration all in one graph, even though like dimensionally that's crazy, right? What is the voltage? What's V voltage on R here? It's IR, right? So the voltage on R, it pretty much looks the same, right? I'll graph it down here just for the sake of having a different, level. But this would be, V equals to IR. That's the voltage dropped on the resistor, right? Which is what? We've got Q naught over C times e to the minus t over RC, right? The R cancels. That would be the voltage on the resistor. What's the voltage on the capacitor? Well, remember it's what? It's Q over C, right? So Q over C, is that the same? I mean, it should be the same, right? Duh. So Q over C is what? Q naught e to the minus t over RC divided by C, right? Well, of course, we're back to the same formula, because the voltage on the capacitor is equal to the voltage on the resistor in this circuit. It's not especially interesting. This becomes more interesting in like the next example. I'm just trying to show you it all works together. Let's see here, what else can I tell you? What happens to the current as time goes to infinity? What's the limit of the current as time goes to infinity? Yeah?
From 0 to the current.
From what?
Or, I guess
As the time constant goes to infinity?
Well, the time constant's fixed. Like the time constant is whatever it is for the given circuit. We're not thinking about varying the resistance or the capacitance, right? So like, for example, let me be more specific here. Example 1. If I had, for instance, a 3 microfarad capacitor and it was discharging into a, 4 kilo ohm resistor, right? If that's the situation, the time constant here is RC, which is 3 microfarads times 4 kilo ohms, which gives me 12 milliseconds. Because micro times kilo is milli. 3 times 4 is 12, so 12 milliseconds. If you have a 3 microfarad capacitor and a 4 kilo ohm resistor, you're discharging through that resistor. It takes about 60 milliseconds for it to be almost completely discharged.
A farad times a second.
Apparently. I mean, yeah. Why is a farad times an ohm a second? Yeah, that's the funny thing is like the units, they do sneak up on you. I mean, this is a fun game to play now that you started it. So last time, I talked to one of you about this after class. It's worth talking about again. So we had formulas last time, like energy stored in a capacitor, right? And so the energy stored in a capacitor was, on the one hand, 1/2 CV squared. We also had the Q squared over 2C formula, I think. And we also had the 1/2 QV formula, right? On the other hand, for power, we have IV, we have I squared R, and we also have V squared over R. Right? These are formulas we have for power dissipated in a resistor and the energy stored in a capacitor. These equations tell you weird relations between units if you look at it. You see, because like units for energy are what? Joules, right? So a joule has to apparently be equal to a farad times a volt squared, but it also has to be equal to a coulomb squared divided by a farad. I know, it's annoying. The units for capacitance are F. Like here we're talking about a capacitor. Here I'm talking about a coulomb. Understand the difference. I'm so sorry, but it's not my fault. I just teach this course. I don't make the letters. And then, I mean, I could change all the letters to protect the innocent, I guess, but you probably don't want me to do that. Coulomb times volt. So these these are relations between volts and farads and coulombs that maybe aren't obvious. This, on the other hand, is a watt. A watt is equal to, an amp times a volt, right? And it's also equal to an amp squared times an ohm. And it's also equal to a volt squared divided by an ohm. Whew, goodness. Ugh. Just feel filthy now. It's got that disgusting top-hattedness on my hand.
Thank you.
Nice pencil. Pencils I have in my office are not as nice. I got those annoying like yellow ones from the department. You know what I'm talking about? The ones that the garbage. I mean, they're free, so I can't complain, but I guess I am. But a watt is also a joule over second, right? Which is also a kilogram meters squared over second cubed. Because a watt is a joule is a Newton meter, which is a kilogram meters per second squared times meter. So that's, I don't know. We could be here all day. The way units are related is sometimes unanticipated. Every one of these equations gives you a bridge between different units. Any questions? And then I don't know. I always forget the units on like the epsilon knot. What's that? What are the units on epsilon knot? I mean, we know that a Newton, we know that the force is equal to like 1 over 4 pi epsilon naught, right? Q1, Q2 over r squared. So like that tells me that a Newton is equal to a Coulomb squared over whatever the units are for epsilon naught, right? Whatever they are, times meters squared. So apparently the units for epsilon naught are equal to a Newton meter squared over, Coulomb squared, which, if you really want to, we could get nuts and convert to like farads and volts. Anybody? That would be a nasty test question, wouldn't it? Right? Epsilon naught in terms of volts and farads. What's that? I'm too kind for that. You've taken my test? But anyway. All right, let me stop misbehaving. Let's get back to, so this is it. This is the discharging capacitor. There's really not much to it. In terms of calculus, it's just separation of variables. We could have done this in our sleep at the end of calculus 1, right? Not a big deal. Now, of course, if you actually put in numbers, it can look uglier, but there's really not that much to it. Now, let's put a capacitor and a resistor in a circuit with a voltage source and try to work that out. The principles remain the same. In terms of, we use Ohm's law for resistors, and we use that the voltage on the capacitor is governed by its defining relation, right? That C is equal to Q over V. So if I have something where I've got, say, a voltage source, yeah, I'll get it eventually, like this, right? And I got a switch, and I'm going to have a resistor here, let's say, and a capacitor there. It doesn't really matter which order they're in, right? And so initially, we want to let the capacitor be uncharged, all right? Then, so initially initially uncharged. So initially, capacitor uncharged, all right? And, okay, initially each capacitor uncharged, and then we're going to close the switch at time t equals to 0, just to keep it simple. I mean, we could close the switch at some other time if you wanted to, but we'll just close it at time 0 just to make the math a little bit prettier. So we got a capacitor here, we got a resistor here. Then the question is, what happens? What's the current that flows after you close the switch at time 0? How do we work this out? All right? So let's work it out. Man, I was just looking at what Dr. Budaras was doing in Physics 1, like class, and I feel like I got to up the game in here. I need to, I don't know. I need to make it a lot worse. Like, this is too easy, like what we're doing right now. It's like way too easy. Maybe I should add like a spider of resistors or something. Put everything, I don't know. It's like a chain. It's like a chain falling off a desk. And like some of the mass is slipping, but others not. It's like really cool.
Yeah, let's test one time.
It's really cool. I mean, that's in my differential equations notes. Why am I not doing that in 231? That would make 231 more fun. Circuit falling off the desk. I like that. Very good. Very good. Very good. All right, so let me make sure I follow the right sign conventions here. Oh man, seriously? Dudes. I'm past my notes. Rats. All right, we're just going to have to work it out. That's bad. Well, it's okay. I'll figure it out. If I do something wrong, you guys let me know. I mean, we'll figure it out in the end because we'll get a crazy solution. Then we'll go like, ah, I've missed a sign somewhere in the setup. So let's let the current go that way to be defined as positive, right? That means that the current goes like so. And let's think about this. How is I related to the charge here now? You're like, well, last time you said I was minus dq dt, so isn't it still the case? It's not. See, now I is plus dq dt. Because when the current's positive, it is increasing the charge on the capacitor. Previously, we were taking charge off the capacitor. That's why the current was minus dq dt there. So the relationship's different. So that'll catch you off guard if you're not watching out for it. So I is dq dt. And so we just do Kirchhoff's voltage law, KVL. And what's that look like here? Where'd my blue markers gone to? Are you guys excited about the weekend? Okay. Is there something happening this weekend?
Sleep.
Sleep? Oh yeah, I remember sleep. See here. And what?
Midnight Mayhem.
Midnight Mayhem. What's that?
Hockey.
Oh, hockey. Oh. That's the thing where people fight each other on the ice, right?
Yeah, that's the one.
Okay, very good. My friend Crazy Paul, although he denies this now, but he used to say, yeah, well, technically his name isn't Crazy Paul, but I call him Crazy Paul, to distinguish from my other friend who I refer to as Somber Paul, these descriptors being somewhat accurate. Crazy Paul has a number of interesting features. He will just try to get hugs from random people. I've always pointed out there seems to be a disproportionality in the hugs between pretty girls and less pretty girls. He denies this. And if you confront him about this, he will immediately hug you, so it's dangerous. And then he will offer anybody but disproportionately pretty girls a ride on his motorcycle. But then if you confront him about this again, you will be invited for a ride on his motorcycle, which is weird. So I never have. But more to the point of this story, there was a point to this. How did I get off on Crazy Paul?
We're talking about hockey.
Oh, hockey, yeah. So you used to always talk about lacrosse, and he said that the whole point of lacrosse was to hit the other person in the neck with a stick. Like that's the whole goal of lacrosse, is to like get the other guy in the neck with a stick. Like that's the whole point. So, but now he says that that's not actually the point. So he seems to like he's mellowed some in his older age, I guess. But anyway.
If he hugged you, did that mean you were a pretty girl?
I felt like if I accept my own theory, I mean, that's a good question though. He also used to like every week he would spend time beating up little children.
What?
I mean, he helped at a dojo. So he never cared for my characterization of his karate habit, but anyway. So I think we do, and this is where I'm getting in trouble. I think it's Q over C here. We'll find out soon whether or not I'm. Yeah, I think that's fine. That's right. I'm a little bit. I doubt myself this time of the day, so I think that's right. So we're taking the sum of the voltage drops. So the voltage dropped on the capacitor is Q over C. Voltage dropped in the resistor is IR, and of course this is the opposite. This is where the energy is coming from, right? So that's a way to think about it, right? Energy in, energy out. So the sum of the energy in and energy out has to be 0. You could look at it that way if you wanted to. Now, okay, so great. Well, this gives us, E. Oh, I'm going to write it this way. R dq dt plus Q over C is equal to E. Now, this is a differential equation we also learned how to solve in Calculus 2, but you're probably a little bit less confident about this one, maybe. Let me just let me reformulate it just a bit to make it pretty. So here we got dq dt plus 1 over RC times Q is equal to E. Yeah, we're good. Yeah. So how do you solve this differential equation? You guys have had lots of time off calculus. You should be really fresh now. You should be ready to go. What kind of differential equation is this? The dependent variable and its derivatives both appear linearly. This is a linear differential equation. First order. The method that we use to solve this typically is the integrating factor method. So what you do is you multiply by the integrating factor. So here, the integrating factor is the exponential of the integral of dt over RC, also known as e to the t over RC. So if I multiply that, I get, I'm going to working myself into the, let me work over here where I have the proper amount of space to work. All right, so we have, so I'm going to multiply the differential equation by e to the t over RC. That's the standard way to solve this. So I have e to the t over RC times dq dt plus 1 over RC e to the t over RC times Q equal to the voltage times e to the t over RC. All right, so then you tilt your head, you squint, search your heart, find it to be true. This is the time derivative of the product of the integrating factor e to the t over RC and the charge Q. Yep.
You divided by R on the left side. Is that correct?
Oh, did I I'm practicing unequal weights and measures. You might want to take me outside this camp and stone me or something here. Let's see here. So yes, E over R, that would be better. Otherwise, it's dimensionally inconsistent. Very good. So I got to divide this whole thing by R. All right. Thank you. Muchas gracias. Let's see here. E over T over RC. There we go. Then, now that we've got a total derivative equal to a function, we integrate both sides to get rid of the differentiation, right? So integrate this with respect to time. Integrate that with respect to time. Oh no. Oh no. And we get integral of the derivative is the thing again. So just e to the t over RC times Q. And then you got to integrate. How do you integrate e to the t over RC? What do you do? We multiply by RC. Right? And then plus a constant. I'll call it C1. I've decided not to try to build the initial conditions in the integration step this time. I'm just going to fit it. All right? Now, you can check me on this. How would you check me on this? If you differentiate what I have right here, right? If you differentiate what I have right there, what happens? What should we get? If this is a legit antiderivative of this up here, when we differentiate what's down here, we should get back to that. And see what happens when I differentiate this? I pull out a 1 over RC, which cancels the RC. And so we're just back to E over R like we want. Yay. And then, finishing move, well, next to finishing move, solve for Q. So we've got Q of T. I added back the T to emphasize the T dependence. The R's, they be canceling, and we get E over the capacitance, E to the T over RC. plus C1, all of that times e to the minus t over RC, which we can simplify a bit, right? So we got Q of t is equal to, apparently, e over c plus C1 e to the minus t over RC, right? Now this is not how we, yeah.
Why is the C going to the denominator? Like, why is E divided by C when C was...
Oh yeah, that's a good question. I don't think there's any good reason for that, except that, yeah, so how about that? That better? Thank you. Very helpful. And is that square with, what's our relation? Let me just check on this. Our capacitance is charge over voltage, right? So charge should be like C times V. So a capacitance times a voltage is a charge. That, dimensionally speaking, algebra aside, we should have been very critical of what I was writing previously, because it's dimensionally inconsistent, right? A coulomb has to be like a volt times a farad, not a volt over a farad. So anyway, great. Now what? We don't want to leave it like that, right? What we want to write our what was our initial charge this time? What's our Q of 0 equal to? We haven't used that yet, right? Q of 0 was equal to 0. It was initially uncharged, right? So we can figure what out this, so what do we got? We got Q of 0 is EC plus C1. What's e to the 0 over RC? What's e to the 0? 1. Okay, so good. So that's equal to 0. What's C1 equal to then? Yeah, C1 is equal to minus EC, apparently. And so what we get? We get the charge at time t is simply equal to EC times 1 minus e to the minus t over RC. There you go. That's the charge at time t on this charging capacitor, where we're charging it in this RC circuit with a voltage source E. So if we were to graph this, what's it look like? Here's voltage equal to EC, right? So it starts out at 0, yeah? By assumption, the charge is initially 0. And after 1, 2, 3, 4, 5 time constants, you notice that? The time constant's still here, even though it's a totally different problem? I mean, it's not totally different, it's kind of related, but here, I think it looks like this. I mean, I'm not doing it quite justice. It should be to like 60-ish% and then like 80-ish, 85%, something like that, 95%, 98%, 99.99 whatever percent. So it's something like this. If I could draw it worth anything. Right, like that. There's your, so as time goes to infinity, what happens? This piece goes to 0, right? Dead. And we just get EC. So that's the charge on the capacitor. Now what's the current then in the circuit? How's that work? What's the current? The current is dq dt. right? And for us here, that's going to be, you know, EC times minus e to the minus t over RC times, by the chain rule, minus 1 over RC, right? Differentiating. The C's, they be canceling. And I think we just get E over R e to the minus t over RC. So what's the current look like? If I had to if I'm so foolish as to graph it, let me erase this Q here and say that the red is the Q. Goodness gracious. So this is Q. The current, on the other hand, starts at its maximum value, let's say here. Its maximum value is E over R to start with, right? And after 5 time constants, I can't. I try. I'm always unsatisfied with my exponentials. They were never exponentially enough for me. Let's see here. But there you go, that's the current. So the current at the initial instant you close the switch, it's the largest it's going to be. And then as the capacitor gets charged, what happens? The current gets smaller and smaller and smaller until finally the current is near 0 after 5 time constants. Remember I told you guys last time that a charged capacitor is like an open circuit? This is what I'm talking about. After the capacitor is charged, the current goes to 0. If the capacitor is in series with other things, it serves like an open circuit. It's almost like the wires are just, you know, disconnected after a while. What's the voltage? What's the voltage on the capacitor? What's the voltage on the resistor? So notice that the voltage on the resistor is just equal to IR, right? Which is simply E to the minus t over RC, right? In contrast, the voltage on the capacitor is Q over C, right? Did I do that right? Yeah, Q over C, which in this case is, you know, E times 1 minus e to the minus t over RC. What happens when you add these two together? What's VC plus VR? What those equal to? Just E. Does that make sense? So what's going on with this circuit is that you've got voltage. I'll draw the picture here again. So what's going on is your voltage source E is getting divided between the voltage dropped on the resistor and the voltage dropped on the capacitor. But the sum of the voltage, you know, this one here, minus to plus VC, and this one here, minus to plus VR, the sum of those two voltages has to be equal to the voltage applied. And what happens is after a long time, the voltage on the resistor is 0 because all of the voltage is dropped across the capacitor. And there's no voltage, essentially no voltage dropped on the resistor, corresponding to the fact that the current flowing is minuscule. These I have to say in a limiting sense, right? Because the current never actually technically stops flowing. There's always a little trickle. But like I said, after 5 time constants, it's less than 1% of what it starts out. Does this make sense? So we can apply the ideas we use today to solve other RC circuits, right? The principle remains the same. We use Kirchhoff's voltage laws, we use Kirchhoff's current laws, and we use the relation for, you know, the defining relation for the capacitor to understand the relation between charge and voltage. The other thing that's a little bit fussy is we also need initial conditions. See, because whether or not the solution as a function of time, it's going to depend on whether or not the capacitors in the circuits are initially charged or initially discharged, like what charge is on them to start with. So maybe next time we'll solve a problem where we have a different situation, and we'll see how that goes. But I think this is a pretty good place to stop for today. So thanks, guys. Have a good weekend.